Welcome, everyone. Today we will be exploring the fascinating world of problem solving by dividing into key principles and reasoning moves. In problem solving, principles are like the fundamentals of truth. They are the basic, the irreducible building of blocks of problems or of concepts. While reasoning, on the other hand, are the logical process in which we apply these principles in order to reach a certain conclusion. In this topic, we will be covering about the powerful techniques like the Pigeon's principle, mathematical induction, and proof by contradiction. We also examine the Polius four steps for tackling problems and learn to distinguish between routine and non-routine problems. Recognizing these unique traits and the best approach for each, our goal is to equip you with a robust toolkit for solving a wide variety of challenges, both inside and outside of the classroom.
Now let's discuss the pigeonhole principle. It is a principle of reasoning that helps us prove the existence of certain outcomes without explicitly identifying them. It shows that when objects are distributed among containers, some repetitions or overlap is unavoidable once the number of objects exceeds the number of containers. Pigeonhole principles has two forms, the direct form and generalized form. Now for direct pigeonhole principle, it states that if n plus 1 objects are placed into n boxes, then at least one box contains at least two objects. For example, among 13 people, at least two must share the same birth month because there are only 12 months in a year. This form guarantees duplication whenever we exceed the available slots. The generalized form states that if n objects are placed into k containers, then at least one container must hold at least n over k objects, where bracket means rounding up. For instance, if 20 students are divided into 6 groups, at least one group must contain 4 students. This version not only ensures duplication but also tells us the minimum number of items in at least one container. Though it sounds simple, this principle helps us reason logically about distribution, fairness, and inevitability. It reminds us that certain outcomes are unavoidable and recognizing them simplifies complex problems. In conclusion, the pigeonhole principle, both in its direct and generalized form, is not really about pigeons but about the logic of placement. The direct form ensures duplication and generalized form quantifies it. Together, they serve as a clear example of how principles and reasoning guide us in solving problems more effectively.
So for the next topic, we're going to explore a powerful problem-solving idea in mathematics called the invariant principle. This principle helps us solve puzzles and problems by looking at what stays the same even though many things are changing. The word invariant comes from the idea of something that does not vary. It doesn't change. So, the invariant principle means in certain mathematical problems, even though operations or moves change the situation, there is at least one property that remains unchanged. This unchanging property is called the invariant. When we can identify the invariant, it often tells us whether a certain goal is possible or impossible. Let's look at a classic example. Imagine a chessboard with 64 squares. On each square, there's a coin. Each coin can either show heads or tails. Now here's the rule. You may choose any two coins and flip them both at the same time. Heads becomes tails and tails becomes heads. The question is it possible to make all the coins show heads? To solve this, let's focus on a property that might not change. Let's count the number of coins showing tails. Now, observe what happens when we perform the operation. If we flip two heads, they both become tails. The number of tails increases by 2. And if we flip two tails, they both become heads. Therefore, the number of tails decreases by 2. And if we flip one head and one tail, they just swap. The number of tails stays the same. Notice something important. The parity of the number of tails, that is, whether the number is odd or even, never changes. If the number of tails is even, it will always remain even. If the number of tails is odd, it will always remain odd. That parity is our invariant. Now, suppose we start with an odd number of tails. Since the parity never changes, the number of tails will always be odd. But if we want all the coins to show heads, that means the number of tails must be 0, which is even. Therefore, if we start with an odd number of tails, it is impossible to reach the goal. But if it is otherwise, then the goal is reachable. Another type of invariants are the monovariants. These are special type of invariant. But unlike ordinary invariants, which stay the same during a process, monovariants either increase or decrease monotonically as the process goes on. In simple words, if something is always going up or always going down, step by step, under certain rules or operations, then we call it a monovariant. Let's make this clearer with an example. Imagine you have n chocolates or number of chocolates. At each turn, you must eat at least one chocolate. Now what changes every turn? Answer is the number of chocolates left. This number is a monovariant because it strictly decreases every time you eat. It can never increase because you can't magically add chocolates back. Eventually, it must reach 0.
Now, we'll be focusing on one of the most elegant and powerful tools in mathematicians' toolkit, which is the principle of mathematical induction. As our CO2 outline shows, mathematical induction sits alongside other key principles like the pigeonhole principle and proof by contradiction. It's crucial to understand that while we use inductive reasoning to spot patterns and form conjectures, mathematical induction itself is a rigorous process of deductive reasoning used to prove those conjectures beyond any doubt. So, what is mathematical induction? So, what is it? Let's think of it as a domino effect. If you can knock the first domino over and you can prove that any domino will knock over the next one, then you can be certain that all the dominoes will fall. So in math, the dominoes are our statements, our Pn, wherein for each number, n is a natural number. So formally, the principle has two non-negotiable steps. First is the base case. You prove the statement is true for the initial value, usually n is equals to 1, so this is like knocking over the first domino. Second, the inductive step. You assume the statement is true for some arbitrary number such as k that is called the inductive hypothesis. Then, you use this assumption to prove the statement must also be true for k plus 1. If you can do both, you've proven the statement for all natural numbers. Let's make this concrete with an example from our material. So first, we have proven that the sum of the first n odd numbers equals to n squared. So first, the base case. For n is equals to 1, the sum is just 1, and 1 is indeed equals to 1 squared. Now, we assume it's true for n is equals to k. So this means we assume that 1 plus 3 plus 5 plus ... plus 2k minus 1 is just equals to k squared. So our goal is to show it's true for n is just equals to k plus 1. So the sum for k plus 1 terms is just the sum for k terms plus the next odd number, which is 2 times k plus 1 minus 1 equals to 2k plus 1. We substitute our assumption, turning that sum into k squared plus 2k plus 1, and as we know from algebra, it simplifies perfectly to k plus 1 squared. And that's exactly what we needed to show. Induction isn't just for sums. It's incredibly useful for these divisibility problems. Now let's prove that 2 to the power of 2n minus 1 is always divisible by 3. So for our base case, we have n minus 1, and 2 squared minus 1 is equals to 3, which is divisible by 3. Now, the inductive hypothesis, let's assume that 2 to the power of 2k minus 1 is equals to 3q for some integer q. Now, for n is equals to 2k plus 1, we have 2 to the power of 2 times k plus 1 minus 1. And we can rewrite this as 4 times 2 to the power of 2k minus 1. So here's the clever part. We use our hypothesis to replace 2 to the power of 2k with 3q plus 1. So this gives us 4 times 3q plus 1 minus 1 equals to 12q plus 4 minus 1. And that equals to 12q plus 3, which is 3 times 4q plus 1. And this is clearly a multiple of 3, proving the inductive step. So when you should reach for induction, use it when your problem involves statements parameterized by natural numbers, proving formulas for sums, products, divisibility, properties, or statements about recursively defined sequences. So the decision is straightforward. If you can establish a starting point and show the truth propagates from one number to the next, then induction is your tool. In summary, mathematical induction is a fundamental proof technique based on a simple but powerful domino principle. It requires a verified base case and a logical inductive step that propagates the truth, making it a rigorous form of deductive reasoning.
Hello everyone, today we're learning proof by contradiction, a method that shows a statement must be true because assuming the opposite leads to the impossible situation. Proof by contradiction works like this. We start by assuming the very thing we want to prove is false. Then we follow the logic of that assumption until we hit a clear contradiction. Because our assumption leads to absurdity, it must itself be false. That means the original statement is true. We have steps involved in contradiction. First, we assume that the statement to be proved is false. Second, we show that our supposition is false. In the last step, we conclude that our actual statement is true because our supposition is false. In this example, we want to prove that n squared is even, then n must also be even. First, let's start with the assumption. In the proof by contradiction, we assume the opposite of what we want to prove. So suppose n squared is even, but n is not even. That means n is odd. So let's express n as an odd number. If n is odd, we can write it as n equals 2k plus 1 for some integer k. Then, let's square both sides. So, we came up with the answer 2 close and open parentheses 2k squared plus 2k plus 1. Then, let's interpret the result. We can see that n squared is equals to 2r plus 1, where our r is equals 2k squared plus 2k. This is exactly the form of an odd number. So, we have shown that if n is odd, then n squared is also odd. But at the beginning, we assumed that n squared is even. Now we end up with the n squared being odd. So this is a contradiction. Therefore, our assumption is that n is odd must be false. So n squared is even, then n must also be even.
Now let's discuss the two important reasoning methods we use in problem solving. First is the inductive reasoning and second is the deductive reasoning. Inductive reasoning is drawing a general rule or conclusion based on specific observation or patterns. It moves from particular to general. For example, we see the number sequence 2, 4, 6, and 8. We might conclude that the next number will be 10. Another example, the sun has risen every morning that we've experienced, so we conclude it will rise again tomorrow. The strength of inductive reasoning is that it helps us spot patterns, form conjectures, and make predictions. However, it does not always guarantee truth. It only provides probable conclusions. In problem solving, induction is often the starting point. We observe data, identify patterns, and propose possible rules. Now, for deductive reasoning, it works in opposite direction. It is drawing a specific conclusion based on general principle, law, or rule. Deductive or deduction moves from general to specific. For example, the rule states that all squares are rectangle. If a given shape is a square, then we can conclude with certainty that the shape is also a rectangle. Unlike induction, deductive reasoning provides definite conclusions as long as the premises are true. In problem solving, deduction allows us to apply rules, test conjectures, and prove results logically. Whenever we use a formula or theorem to solve a specific problem, we are practicing deduction. Both inductive and deductive reasoning are essentials in problem solving. Induction allows us to explore possibilities and create new ideas, while deduction allows us to prove and apply those ideas with certainty. Together, they provide a balanced approach. We discover through patterns and we validate through logic. In summary, induction or inductive reasoning helps us move from examples to generalizations, while deductive reasoning helps us move from general rules to specific conclusion. Both are key essentials and principles of reasonings that strengthen our problem-solving skills. By combining induction and deduction, we are able to reason systematically, think critically, and arrive at conclusions that are both creative and logically sound.
So for the next topic, we're going to talk about a classic problem-solving strategy in mathematics developed by George Polya. This approach has been widely used in classrooms because it helps students become more confident and effective problem solvers. According to Polya, solving a math problem isn't just about getting the right answer. It's about following a process. He outlined 4 important steps that guide us in thinking logically and critically. The first step is understanding the problem. Before rushing to solve, we need to carefully read and analyze what is being asked. This is where we identify the knowns, the unknowns, and the conditions. If we don't fully understand the problem, the rest of the process will be shaky. Next, we move to devising a plan. This is where creativity and strategy come in. We think about what methods, formulas, or patterns might help us. Should we draw a diagram, make a table, recall a similar problem we solved before? At this stage, we are laying out possible strategies. After making a plan, it's time to carry it out. Here, we carefully apply the strategies step by step, or strategy step by step. Accuracy and patience are important. This is where logical reasoning is put into action. And for the last step, is reflecting on the solution. Did our answer make sense? Could there be a simpler way to solve it? This step encourages metacognition, thinking about our own thinking, and helps us learn from each problem we solve. For example, a snail is stuck at the bottom of a 10-meter deep well. Every day, it climbs 3 meters up, but every night, it slips back 2 meters down. The question is, how many days will it take the snail to reach the top of the well? So for step 1, we need to understand the problem. So each day, the snail climbs up 3 meters, but at night, it slides back 2 meters. So the net progress is 1 meter per full day night cycle. But here's the catch. On the final day, once the snail reaches the top, it won't slide back down anymore. So the second step is to devise a plan. We'll track the snail's progress step by step. Each full day night cycle adds 1 meter to its height. When it's close enough, the final climb of 3 meters will bring it out of the well. So step 3. carry out the plan. After 1 day and 1 night, the snail is at 1 meter. After 2 days and nights, it's at 2 meters. And after 7 days and nights, the snail has climbed to 7 meters. On the eighth day, the snail climbs 3 meters from 7 meters up to 10 meters. It finally escapes the well, and since it's out, it doesn't slide back at night. The final step, or step 4, is look back or reflect. So the snail escapes on day 8. If we had only looked at the net progress of 1 meter per day, we might have mistakenly said 10 days. But by reflecting, we see the correction. The snail reaches the top on the 8th day without sliding back. And that's the answer. The snail takes 8 days to climb out of the 10-meter well. This problem shows why it's important to carefully consider the last step when solving math problems. So to summarize, Polya's 4-step method includes understanding the problem, devising a plan, carrying out the plan, and reflecting on the solution. As Lee and Chen in 2015 emphasize, these steps don't just help us solve math problems. They also build critical thinking, logical reasoning, and self-awareness as learners.
Now let's talk about the non-routine and routine problems. In problem solving, not all challenges are created equal. We can broadly classify problems into two categories based on their inherent traits. Let's start with the difference of routine and non-routine problems. Routine problems are those that can be solved by applying a known pre-existing procedure or algorithm. Their key trait is a clear, well-defined path to the solution. The solver typically recognizes the problem as a variation of a type they've seen before and simply executes the appropriate steps. For example, this example includes solving a standard algebraic equation, calculating a derivative, or finding the area of geometric shape using a formula. The focus is on accurate application of a learned technique. In routine problems, it is like when you already know the formula or the steps to solve a certain problem. It is something that you have seen before. Think of a routine problems as a puzzle where you already know the or you already have the instructions. It is a straightforward application of a new known procedure of algorithm. For example, calculating the area of a rectangle or solving a simple linear equation. The key trait is that the path to the solution is clear and well defined, and it is something that you already know. Now, what about the non-routine problems? What makes them different? Non-routine, on the other hand, are those problems that are much harder. They are the problems that you have to think creatively or critically and maybe try different things because there is no obvious method in solving this kind of problems. Non-routine problems are actually characterized by the absence of an obvious, straightforward solutions or end path. They require you a lot to use higher level reasonings, synthesis, and a lot also of trial and error. You might also have to combine different concepts or use a completely new approach. And this is where tools like pigeonholes and proof by contradictions becomes also essential. Now let's consider an example of this kind of problem. Let's compare routine problems and non-routine problems. In routine problems, you might actually encounter some problems like solve for an x in 2x plus 5 is equal to 11, which is part of equations. In non-routine problems, you might encounter problems that such as prove that in any group of six people, there are either three mutual friends or mutual strangers. In those two problems, you can already see the difference. In the first is it is much simpler calculation.
while the second requires a lot of different mode of reasonings. Now, to summarize, a routine problem's trait is that it relies on known algorithm, while a non-routine problem trait is that it demands creative reasonings and also the construction of new solutions back. Understanding these two brings us to the ideas of the first step towards choosing the right problem solving tools for the job.
Problem solving becomes more effective when we apply the right principles and reasoning modes. The pigeonhole principles, invariance, induction, and proof by contradiction each provide powerful ways to approach both routine and non-routine problems. Polya's four steps guide us to think systematically while distinguishing routine from non-routine problems help us decide when to use standard methods or deeper insight, whether through inductive, deductive, or symbolic reasoning. The goal is not just to solve problems but to develop as reflective and critical mathematical thinkers. When choosing a proof strategy, match the method to the problem's core structure. Universal claims over the natural numbers call for mathematical induction. Counting or existence question lean on the pigeonhole principle. Preserve or steadily changing quantities suggest invariance or monovariance, and stalled direct arguments often resolve by assuming the opposite and deriving a contradiction. If no single tool fits Polya's four-step cycle, understand the problem, devise a plan, carry it out, and reflect, provides a reliable framework.